Welcome! Suppose you look at a nice picture on your phone and then you rotate it. The picture then smoothly rotates back so that it is upright again. To do so, your phone has to calculate rotations of the picture for several angles between 0 and pi/2. And for each rotation, it has to calculate where each of the thousands of pixels go. In this video, I would like to show you how this can be done efficiently using linear algebra. First, let's focus on one pixel, let's say at position 2,3, and one rotation angle, let's say pi/4, that is 45 degrees. If we rotate the image over an angle of pi/4 counterclockwise around the origin, point P moves to some point Q. What are the coordinates of Q? Let's formulate the problem using vectors. Given the vector OP, we have to find the vector OQ. In principle, we can first calculate the angle between OP and the positive real axis, add pi/4 to that angle, and then calculate OQ. The problem is that calculating angles is an inefficient operation on computers. It is best to avoid it. Luckily, we can by using linear algebra. To show you how it works, I need two important properties of rotations. The first property is the following. It does not matter whether you first scale a vector and then rotate it, or first rotate the vector and then scale it. The resulting vector is the same in both cases. The second property is the following. It does not matter whether you first add two vectors and then rotate the sum, or first rotate the vectors and then add them. Again, the resulting vector is the same in both cases. Let's go back to the first problem and see how we can exploit these properties. First, note that we can write vector OP as a linear combination of the standard unit vectors E1 and E2. OP equals 2 times E1 plus 3 times E2. So rotating OP by an angle of pi/4 comes down to rotating the sum 2E1 plus 3E2 by pi/4. By the properties of rotations, this is equal to the rotation of 2E1 plus the rotation of 3E2. In turn, this is equal to 2 times the rotation of E1 plus 3 times the rotation of E2. You see that all we have to know is what the rotations of E1 and E2 are. Using the unit circle, it's relatively easy to find out. E1 has components cosine pi/4 and sine pi/4, both of which can be calculated explicitly, and E2 has components cosine 3 pi/4 and sine 3 pi/4, which also can be calculated. So, to find the rotation of vector OP, we simply take 2 times the first plus 3 times the second. Hence, we find that the coordinates of Q are -1/2 square root of 2 and 5 square root of 2. This may seem like a lot of work, but the procedure works for any vector v. Let me show you. If v has components a and b, then we can write it as a times E1 plus b times E2. The rotation of v is a times the rotation of E1 plus b times the rotation of E2. And since we already know the rotations of E1 and E2, we can easily calculate the rotation of v. You see that we only need multiplication and addition once you know where E1 and E2 go. Computers are very good at performing addition and multiplication, so this is how your phone can calculate rotations of a picture efficiently. The essential point of the calculation is that rotation behaves well with respect to vector addition and scalar multiplication. It is an example of a so-called linear transformation. To be precise, a transformation T from Rn to Rm is called a linear transformation if it has the following properties. T of c times x equals c times t of x for any vector x and any scalar c, and t of x plus y equals t of x plus t of y for any pair of vectors x and y. The first property means that it does not matter whether you first scale a vector and then transform it, or first transform it and then scale it. The second property means that it does not matter whether you first add vectors and then transform, or first transform and then add. Any rotation around the origin has both properties, so it is an example of a linear transformation. An important consequence is the following. Suppose you pick a basis for Rn, so that you can write any vector x in Rn as a linear combination of the basis vectors, then Tx is a linear combination of the transformed basis vectors with the same coefficients x1 to xn. This means that if you know how the basis vectors transform under T, then you can easily calculate the transformation of all other vectors. We exploited this property in calculating the rotation in the example, and you will see more applications of this property in the rest of the week. Let me end by stressing that the requirements for a linear transformation are very strict. There are many transformations that are not linear. As counterexample, consider the transformation on the slide. You can easily check that this is not a linear transformation. For example, if you apply t to 2 times the vector 3, 4, you get the vector 48, 14. If t were linear, this should be equal to 2 times t of 3, 4. However, if you calculate this, you get 24, 14. These vectors are not equal, so t is not a linear transformation. In the exercises, you can see if you can tell apart linear transformations from non-linear transformations. Good luck.